So today we will talk about the reactive applications. How many of you have heard about reactive applications? Cool. And how many of you have been focused on building reactive applications? Great. So I think some of the principles that I am talking about today, you may already be well versed with, but let's see if I can add some value to whatever you know. So small introduction about me, right? So I have been a part of Naldus, which is now a part of Nasdaq, right? So we grew the company from 20 employees to around 250 employees. Primary focus was always Scala. We have been focused on functional programming, right? Some of the things that I do for my clients is basically help with them with their architecture, their digital transformation initiatives, as well as we do impart training to various people on Scala. The agenda for the today's meeting is introduction to reactive applications, reactive principles, reactive architecture patterns, implementation details, and then we can park some questions if you have, right? So we can discuss about those questions. So these are some of the keywords, right, that you may be hearing a lot, right? So it's distributed, asynchronous, event-driven, high throughput, concurrent, elastic, resilience, low latency, scalable. So all these applications, right, that we are building right now, they should basically adhere to all these principles to be more responsive, right? And reactive applications has certain principles, okay? So all the reactive applications are built on these principles, and these principles are pretty simple. Let's see what reactive applications are. So nowadays, right, when we are building an application, everybody talks about that the application should be scalable. So that is the first need. The second need is because a lot of these applications are getting deployed on cloud, okay, so it should consume less resources. It should produce more, but consume less resources. So optimum cost with maximum performance. Ability to handle failures, right? Your application should always be available. Your application should be able to handle failures. Distributed. Nowadays, right, the load requirement is so much high, right, that you cannot go with the old stack of having a monolithic application or basically an application that runs on few servers with load balancer in place. So your application should be distributed, right? So distributed, when I'm talking about distributed, it means your storage is distributed, your compute is distributed, everything is distributed. And your application should basically perform consistently, right? So that is one of the aspects that also determine the usability of the application. If your application is not consistent, nobody is going to use it, right? So it cannot be that one day your application is working fine, the next day your application is down, then again it comes up, right? So it has to show a consistent behavior. Now let's look at some of the principles of reactive architecture, right? So the first principle is that your application should be responsive. So it should respond in a timely fashion. So whenever a user is basically working on your application, right, he expects that your application is basically supposed to do what it is supposed to do. It should be consistent and it should react at a timely fashion, right? So time is very important, right? You can say that your functionality is working fine, but if there is a delay, then it is not going to help the users. Second is your application should be resilient. So how many times, right, we are working on Netflix, right? We are watching Netflix, and sometimes the list goes away. But you can still use other parts of the application, right? So you can still browse through the episodes, you can still browse through the movies, or you can see the latest movies. But one part of the application is not working, right? But it doesn't hamper the usability of the application, right? One part is hampered, but the other parts are working fine, right? So the application is resilient. Okay? It should basically respond to the failure. Now, imagine when we are building any application, right? You have to make sure that you are handling failures, right? Because failures are going to happen. So don't treat failures as second-class citizens. The failures are first-class citizens, right? Because all the applications that you are built, you have to assure that there may be network disruption, there may be other issues, so your application may go down, right? So we have to handle for those failures. Your application should be elastic, right? So nowadays, right, when so I was working with a customer, right, who is building an e-commerce application, and whenever there is a sales event, the application load goes enormously high. So it is basically difficult if you have to basically provision servers on the go. And initially what they used to do was they used to basically build a backlog of servers, right, that can actually cater to the needs when the load will go up. But sometimes the load is so high that even those resources cannot basically scale up. So what you need to do is, right, you need to basically plan for elasticity in your application, right? So as soon as your load goes up, your number of servers or whatever resources you need, they should also go up. Similarly, there are dull periods as well, right? So your application should be able to scale down to preserve the cost. Now, the other thing is message-driven, right? So most of the time, right, if we talk about, so think of it from the perspective, right, that everything, right, when you are, so most of the applications that we used to build earlier, right, so they were CRUD-based, and they were always blocking operations, right? Now, blocking operations basically decrease the performance of your application. So you cannot, even though you are basically building concurrency into the system, or basically you can run it with more resources, but there is a limit, right? Your performance will not grow exponentially or linearly when you increase the resources, right? So what we have to do is, we have to basically use async communication, and more, right, whenever the components talk to each other, they should be message-driven communication through async and non-blocking messages. Now, a lot of people confuse about reactive programming and reactive systems, right? So reactive systems are those which basically, which cater to these 4 principles, right? And reactive programming is the way, right? So most of the languages, especially Scala, right? And then RX Java is there, Resilience 4J is there, right? Which helps you to perform certain operations with the stream of data, okay? So, and then there are futures, promises, async. So a language which provides all these features is basically a reactive programming language, right? But when you're building, so reactive programming languages are good use case for building reactive applications. So some of the architectural patterns for reactive applications, right? Now everybody talks about domain-driven design, right? So what you have to do is you have to identify the components of your application and basically build your microservices around that. So the bounded context, right, is one of the terms that comes again and again within your domain-driven design. You have to identify the bounded context of your services that you are building. Your services, moreover, right, what you have to do is when you are building your services, you have to identify, how do you identify the bounded context, right? One of the very popular techniques that we use is event storming, right? So what you have to understand is that how events are flowing all throughout your system. Once you determine that, you will be able to basically see what are the events that crosses the boundaries, right? And then you mark your boundaries, and then see what domain model will basically suit your bounded context. Now, one of the things that that always comes up, right? There are a lot of people who are focusing on microservices, right? And we see that microservices is kind of a hot architecture that everybody is following, right? But most of the times I work with clients, okay, they do not exactly know how to build microservices correctly. The problem is that, so I was just giving an example, right? So I was basically called for consulting for a particular client, and they said that we are building microservices, right? And all they were doing was they have different components running which were talking to the same database. So when we are talking about microservices, right, there are few isolation principles that we have to be very, very focused on, because these principles actually guide how your microservices will behave. So the first one is isolation of state, right? So your state for a microservice should be totally independent. There is no other microservice which can modify the state of the microservices that is in question. So your state should be independent. Similarly, if I talk about space, the microservices can be deployed independent of the other microservices, right? So other microservices should not care where the other microservice is deployed, right? You can replicate your microservices across data centers to give more scalability, right? It should not matter the working of the microservice. Similarly, they should be isolated in time. A microservice should not depend on other microservice, right? So they should be basically independent. Right? A request, right, going through the other microservice, we should not basically wait for the response. Okay. So how do we implement that? We can use async communication or message-driven communication so that these are isolated in space. And then isolation of failure, right? So most of the time, right, we see about that there is a particular component, right, which is calling another component. If another component is unavailable, your first component also goes down, okay, because there is a tight coupling between those two components. So we should basically isolate the failure as well, right? So failure in one microservice should not impact the other microservice. Now another very popular pattern, right, that is deployed is event sourcing and CQRS pattern. And I think a lot of people will be familiar about it, right, because a lot of applications are built nowadays using these two patterns. Now, event sourcing is different from event-driven design. Event sourcing is basically keeping your events, right, keeping track of your events, all the applications that are happening, and keeping an event log, right? So all the events are tracked, and they are utilized to basically generate your state. One of the common examples, right? So if you see, let's say in the banking system, right? When we basically record any statement, okay, they do not generate a total. What they do is they basically keep on generating the events, right? So it's like you have deposited money, you have withdrawn money, somebody else has deposited money, right? So they are basically keeping an event log. And when you are basically looking for the balance, they actually generate the balance on the go. Similarly, event sourcing is a technique, right, where you keep on track of all the events, right, by logging them and storing them in the event log. It gives you a lot of benefits, right? So you can always audit your application. You can replay the state. You can also basically build n number of views from the event data that you have. Now, if we look at event sourcing, right, basically the philosophy is think a little, write, and then think later. So the idea is that, so every event, every transition that you are doing, right, is a small write into the system, right, and it's an append-only log. So you basically raise a command. This command may be a valid command or may be an invalid command, right, and then you log the event, or you write the event, right? After you write the event, right, you send the response back to the user. Similarly, when you want to generate the state, what this event will do is this event will affect a state, right? So for example, add item to your cart. So add item is basically a command, but it will generate an event which is item added, which will be persisted in your event log. And this item added, right, will actually update your state. Now, so I was talking about commands and events, right? So what is the difference between a command? Command is like submit order, right? Add item. A request, right? A request to do something. It may fail or it may affect some change in the state. But event is always a fact, right? Event has already happened. So it's like item added, or basically the item checked out or order placed, right? So you cannot roll back an event, okay? So that is what event is. So event basically become facts for your application, and you can do a lot of things with these events. And then another pattern we talked about is CQRS, right? So what is Command Query Responsibility Segregation Principle? Okay. Now, so we say that we have already distributed our domain model into different microservices, right? But it is important for us to understand that you have to basically make your individual microservices also very, very efficient. And the way to do that is basically using a CQRS model, right? CQRS model is basically different from event sourcing, right? So a lot of people also say that CQRS and event sourcing are same. You can use event sourcing without CQRS, or you can use CQRS without event sourcing as well. So command is for updates, right? So any updates or writes that are happening in your persistence layer is through commands. And query is read only, right? So one of the benefits that you get from CQRS is that you can scale your writes and reads differently. So you can have n number of storages, right, where you can write. So let's say if you have a write intensive application, okay, and there are not many writes happening, what you can do is you can say that my write side have more resources and my read side will have less resources, right? So that gives you more independence. And if you look at some of the things going on in big data world, right? So everybody talking about Snowflake, everybody is talking about BigQuery, right? Now, what do, right? So they actually separate out the storage with the compute, right? So you can grow your storage and you can grow your compute as you require. So CQRS is an important pattern, right? I think it will take a lot of time to basically describe that. Now, another thing that we keep referring to is actor model, right? So actor model is a very, very important concept. So if we talk about Akka, right, and it was originated from Erlang, but actor model, what does actor model provides you? Right? So actors are basically, it provides you concurrency without locking, okay? Without blocking, right? So all you do is message passing between the actors, okay? And actors are owner of their own state. So any other actor cannot modify the other actor's state, right? So basically it gives you, and most of the time when we are using Scala, we are using immutable variables, right? So that's make your code less error prone and helps you to build your application faster, right? So it gives you simple concurrency, it gives you simpler distribution, right? Because because of location transparency feature in Akka, you can actually distribute your across different clusters, right? And it provides you fault tolerance because actor models can give you supervision, right? So you can have supervisor actors or supervision strategies to basically manage your actors better. And now, so Akka type library, right, which has been launched, it is a very good library to define the behavior of your actors, right? So you can try it out. And then futures, right? And so this is still a problem, right? We know that future exists in Java, futures exist in Scala. Futures are more intuitive in Scala, and it helps you to build your application better. But I see still a lot of people, right? They do not use future, right? They basically start building the applications using the blocking operations, right? So whether it's REST API or any blocking applications. And then, so for resilience, right, I would like to discuss about the circuit breaker pattern, right? So what circuit breaker pattern is? A circuit breaker pattern is a pattern that prevents cascading failure. Okay. So let's say you are calling a lot of external services from your application. Okay. Now, it is recommended to have a circuit breaker pattern being applied across all your external calls, okay, so that your application do not fail in case the external service is unavailable, right? What happens is when you have a blocking context, your application gets blocked, your application threads get blocked. And if you do not take care of it, right, if there is no circuit breaker pattern, we will keep on basically trying to connect to that services, right? Multiple requests coming, and they are going to the other service, and everything is getting blocked, right? So the idea is that we have a proxy which is monitoring how your service calls are being made, how your external calls are being made. So circuit breaker pattern has 3 stages, right? So it has an open, half open, and closed. Okay. So when it is in closed stage, everything is going fine, right? Your requests can go through. Okay. But let's say there is a problem with the system, right? The service did not respond, the external service didn't respond. Okay. Then it will basically go into a half open stage, right? Where it will say that I will try with 2 or 3 requests. If those do not grow, then it will open the circuit breaker. Then none of the calls will go through to the external system, right? So it will help in self-healing. And then once the service gets back, right, it will try to again do the number of calls, right, that you have stipulated in the pattern. And then if those are successful, it will again make the circuit breaker closed. So all the calls can go through, right? Now it is very important to, so this is one of the pattern that you can use to provide resilience, right, between different components, and make sure that your external calls are wrapped around a circuit breaker pattern. Then there is another bulkhead pattern, right? And what this bulkhead pattern talks about is basically that you isolate the failures, right? So you basically divide your services into different resources, right? So that if one of the resource set is under the gray cloud, at least the other resource sets are working fine, right? Because let me give you an example. So we were working for one of the clients, right? Now, what they were trying to do is, so they have different customers. It's a multi-tenant application. Now, what happened was, once the request, right, so one of the client, they started consuming all the services. And now what happened was that all their resource pool was servicing this particular client, okay, which caused all other clients to basically go under the weather. Okay. So the idea is that you should have multiple set of resources, right, or multiple instances to serve different clients, right? So, and that is the pattern that we implemented there, and they basically stopped facing that particular problem. So, I think I'm already over time. I wanted to discuss about the implementation detail of CQRS through Akka and Cluster, but I think that we can take on the next course. Thank you guys. Open for questions.